welcome back to adiabatic instabilities and stability. This morning we have considered the linear adiabatic radial wave equation. That means we have considered radially symmetric, spherically symmetric adiabatic perturbations of a star. We have considered the perturbation problem, and in the end we have finally got a criterion for instability with respect to radial adiabatic perturbations, which was expressed in terms of the mean adiabatic index. So once the mean adiabatic index falls below 4/3, we found that there is an instability. Be careful, this needs to be formulated in very careful. It means that gamma below 4/3 means it's sufficient for instability but not necessary. Okay, so once having this stability criterion, which sounds within the framework of our mathematical derivation rather counterintuitive, what is the physical meaning, or how can we get a physical intuitive picture why it is the adiabatic index and why it is the value of 4/3 below which a star will become unstable, below which a star will then start either to expand or collapse, depending on which situation we actually have. So let's finally introduce some intuitive argument why the critical value of the adiabatic index should be 4/3 for dynamical instability. For this purpose, let's consider again hydrostatic equilibrium. The instability must be of mechanical nature because we have only considered the mechanical equations when we derive the stability criterion. So we can have to consider the mechanical equations for getting an intuitive picture why gamma falling below 4/3 means that the star is unstable. Hydrostatic equilibrium in usual way, dp by dm is minus g times mass over the power 4 of the radius. In the usual way we use or estimate this equation, we replace the gradient with respect to mass simply by the ratio of pressure over mass, and we keep the mass constant. And once we keep the mass constant, this means that the pressure scales with the radius to r to minus 4. So if we want to keep our star in equilibrium and we try to compress it, then for keeping it in equilibrium, then the radius or the pressure should scale with radius with r to minus 4. So if we compress it and we want to keep it, want it to stay in equilibrium, then the pressure has to rise like r to minus 4. Now, if we compress or change the volume of our star, then also the thermal pressure will change. And if we have adiabatic changes of state, if the compression or the perturbation is fast enough such that the matter cannot exchange heat with its surroundings, then the pressure will go like the density to the power gamma adiabatic. D log P by D log rho is gamma adiabatic, and if we integrate this relation, then the pressure should go with the density to the power gamma adiabatic. This is derived from the thermal equation. This is mechanical equilibrium, and this is the thermodynamics, which gives us this relation or this dependence of the pressure on density. Now, estimating the density by mass over the volume of the sphere, then we have, keeping again the mass fixed, that the pressure will rise once we have an adiabatic change of state with the radius to the power minus 3 times gamma adiabatic. Now, we can have two situations. Either the pressure rises faster than it would need for keeping it in equilibrium. What happens if the thermal pressure, once we compress our star, and the thermal pressure rises faster than it would need to rise once it is in equilibrium, then it will restore the perturbation. Also, the opposite happens if we decompress our star and it falls off faster than then R2 minus 4, then needed for equilibrium, then it will have a restoring force. It will turn back to the initial state. If it rises more slowly than R2 minus 4, then it will not be restored, but it will collapse, or in the other direction, then it will expand if it rises more. If it rises faster than 10 to minus 4, if we decompress it. So the condition that it rises faster with compression, it rises faster than R2 minus 4 would mean that 3 gamma adiabatic has to be bigger than 4. And this means for stability, 3 times gamma adiabatic has to be bigger than 4, or gamma adiabatic has to be bigger than 4/3 for stability. And of course, the opposite for instability, we have that gamma adiabatic is smaller than 4/3. So we can explain it in an intuitive way simply by considering how the pressure scales with radius in equilibrium and how the pressure scales with radius once we adopt a thermal reaction of the thermal pressure onto our compression or onto our perturbation. Okay? Stability means for compressive perturbation, thermal pressure rises faster than required for equilibrium. This means minus 3 gamma adiabatic has to be smaller than minus 4, or gamma adiabatic has to be bigger than 4/3, and vice versa. Instability is found once the adiabatic index is smaller than 4/3. So this is an intuitive explanation for the criterion we found on using lots of mathematics, using the properties of the perturbation equations, going through an equivalence with a functional principle for the perturbation equations. This is a simple explanation why the critical value for gamma adiabatic should be 4/3. Okay, now we are finished with the radial linear adiabatic perturbation. The next step, of course, would be the non-radial linear adiabatic perturbations. So I would need the next file. So what we are talking for today, for the rest of this lecture, will be non-radial adiabatic perturbations. And to start with, we start at the derivation of the general form of the non-radial perturbation equations, which we have considered, I think it was yesterday. And we have derived the system of linearized version of the momentum equation. This is the first component of the momentum equation we had derived yesterday. The second and third one was taken to be replacing the corresponding terms in the mass conservation equation. So the second equation here is the equation for mass conservation. Already replaced are the theta and phi components of the velocity, and we have already applied the expansion in terms of spherical harmonics. So these are the two equations which are left, the radial component of the momentum equation and the mass conservation equation, already replacing the replacing the derivatives with respect to angles theta and phi, and having performed already the expansion in terms of spherical harmonics. Okay, one equation is left here, which needs to be considered once we consider adiabatic changes of state. This is the perturbed version or the linearized version of the potential, the Poisson's equation, which gives the Laplace operator acting on the Eulerian perturbation of the potential, and on the right hand side we have the Eulerian perturbation of the density. Again, here we have already taken into account the perturbation or the expansion in terms of spherical harmonics, and the derivatives, the angular derivatives, gives this factor L times L plus 1 in the second half or in the third term of the Poisson's equation. Okay, thermal equations are not necessary here because we want to deal with adiabatic changes, so we can abandon both the energy conservation equation and the energy transport equation. These are the 4, 1, 2, and this is of course the second order system. So this is the fourth order system governing adiabatic linear non-radial pulsations. Okay, now, well, we have to arrive what we want to do now, or the aim for this, the first half of this lecture will be to get to the standardized form of the non-radial adiabatic equations. And to arrive at these equations, we replace the Eulerian velocity perturbation by the Lagrangian displacement psi r, of course only the radial component, and the relation between the Eulerian velocity perturbation is given by this equation. The Eulerian velocity perturbation is simply the Eulerian time derivative of the Lagrangian component psi r. Okay, this is one transformation or one assumption we make in order to arrive finally at the standard form of the non-radial adiabatic equations. The second one, of course, is the assumption which is basic to all of what we are saying here. It means that we require adiabatic changes of state. This has been discussed already in connection with radial perturbation, and it means that the Lagrangian variation of temperature relative to the unperturbed value is given by nabla adiabatic times the Lagrangian pressure perturbation divided by the stationary pressure stratification. Okay, now to arrive at the standard form, we first of all express the Lagrangian temperature and pressure perturbation in terms of the Eulerian perturbations. I remind you, we have in the last lecture we have derived the general relations between Lagrangian and Eulerian perturbations, and we apply now these relations to the case delta t, delta p, and relate the Lagrangian perturbation to the Eulerian perturbation. Also, this equation is relating Eulerian velocity perturbation with Lagrangian displacement is given in the general discussion of the relation between Eulerian and Lagrangian perturbations. Okay, so what we arrive with is delta t is t tilde Eulerian temperature perturbation plus the Lagrangian displacement times the gradient or the derivative here with respect to radius of the stationary or the hydrostatic temperature stratification with a parallel or an analog relation for the Lagrangian pressure perturbation given in terms of the Eulerian pressure perturbation and the Lagrangian displacement and the hydrostatic pressure gradient. Okay, so we may now replace, or we may now take both our condition of adiabatic changes of state and reformulate it in terms of the Eulerian perturbations. And what we see then is there is first of all a relation between the Eulerian perturbations of temperature and pressure, which is pretty similar to that of the Lagrangian ones, but there is an additional term which comes from the Lagrangian displacement times the respective gradients of temperature and pressure. So we obtain T tilde over T naught is nabla adiabatic times P tilde over P naught, parallel to the Lagrangian one, minus now the Lagrangian displacement times an expression which involves both the temperature gradient of the background model and the pressure gradient of the background model. So it's, you see, when considering these equations, it is important whether we require the Lagrangian entropy variation to vanish or the Eulerian perturbation of the entropy to vanish. They differ by a term which goes with the gradient of the entropy, or in this case with the gradient of the background temperature and pressure. So this is certainly very much different from this equation because there is an additional term. So one should be careful which type of the perturbations have to be set to zero. Here the correct way would be the Lagrangian, to put the Lagrangian perturbation of the entropy equal to zero, because these two issues are different. Okay. Note that, well, this here, this bracketed term might now be identified. I will not go into the detail. This might be identified with the gradient of the entropy. We could also have written delta S equal to 0 and then relate the Lagrangian perturbation of the entropy and the Eulerian one, and they differ, of course, with by the Lagrangian displacement and the gradient of the entropy. Maybe I should write down it here somehow. Delta S equal to 0. This means the Lagrangian perturbation of the pressure of the entropy equal to 0 is equal to, now we replace the Lagrangian perturbation by the Eulerian perturbation. This is S tilde plus psi r times ds naught over dr, and therefore we can identify this bracket apart from the factor of the specific heat with the entropy gradient of the hydrostatic model. Okay, then in the next step we will make use of the equation of state in the following form, where the density, the relative Eulerian density perturbation is related to the relative Eulerian pressure and temperature variation. Of course, we have our well-known coefficients alpha and delta appearing in this relation. It's simply based on an equation of state where the density depends on pressure and temperature, or where we choose pressure and temperature as a thermodynamic basis. What shall we do with all these equations? Well, we can now replace the density perturbation by the pressure perturbation and the temperature perturbation, and our condition that we are dealing with adiabatic perturbation. We can then replace also the temperature variation by pressure variation and the Lagrangian displacement. So we can, by this means, we can get rid of density perturbation and temperature variation This means in the original equations, well, we are left with, of course, the potential perturbation will still be there. Density will be replaced by pressure perturbation, and temperature will be replaced by pressure perturbation and Lagrangian displacement. So we are left with pressure perturbation and Lagrangian displacement here. Well, here there is nothing to do. In the first equation, the density perturbation will be replaced by the pressure perturbation. So we are left with pressure perturbation, the velocity perturbation, or alternatively the Lagrangian displacement and the potential perturbation. So we have enough equations for the remaining variables which are left after these transformations have been done. Okay, so now we introduce a definition. We introduce the quantity A, which is proportional to the entropy gradient. We saw the entropy gradient is more or less this bracketed term, which appears in the relation between temperature and pressure perturbation. This is this bracket here. This bracket is proportional to the entropy gradient of the hydrostatic model, and we define essentially this bracketed term as a quantity A apart from a factor delta. This is delta coming from the equation of state, and this of course is then also proportional to the entropy gradient of our stationary model. Now we change in this expression, we change the thermodynamic basis from temperature to pressure to density and pressure by means of the equation of state. The relative gradient of the density is expressed by the equation of state in terms of the relative gradient of pressure times the coefficient alpha minus delta times the relative gradient of the temperature. If we do that and insert this for the temperature gradient, that means we replace the temperature gradient by pressure gradients and density gradients and sum up all these terms, then we end up with an expression for the quantity A, which contains the relative density gradient and the relative pressure gradient and a coefficient which goes with minus alpha plus delta times nabla adiabatic. Well, this can be given a more compact form, this quantity. This is, we have already derived this expression in one of the previous slides. The minus alpha plus delta nabla adiabatic is 1 over the adiabatic exponent gamma adiabatic. Okay, so we can rewrite the quantity A by relative gradient of density, relative gradient of pressure, and the adiabatic exponent gamma adiabatic. Keep this in mind, we will use this quantity later on. Well, then we introduce some new variables, some transformation, and we will then end up with the standard formulation of the non-radial linear adiabatic problem given the first time by Ledoux and Wallraven. So we introduce a new variable u by multiplying the Lagrangian displacement with r squared, and we introduce a new variable y by dividing the Eulerian pressure perturbation by the hydrostatic density stratification. Then we introduce the gravity using the gravitational potential. There is nothing secret behind it, which is according to hydrostatic equilibrium given by minus 1 over the density times the pressure gradient. So this is introduced here in the notation of Ledoux and Wallraven, and of course we do as we did every time, we adopt the time separation as proportional to the exponential of I omega t, and omega is our eigenfrequency or our eigenvalue of the problem. Okay, if we do that and adopt this notation, then we end up with the following system of equations. Well, the first one, the y was the pressure. So this is the Ledoux and Wallraven formulation of the momentum equation. The second one is the formulation of the mass conservation according to Ledoux and Wallraven, and the last one is the formulation of the linearized version of Poisson's equation. So we have three variables. We have the y and u as a variable, and we have the potential and its derivative as the new variables. This is the formulation according to Ledoux and Wallraven. Of course, we have to satisfy boundary conditions. At the center, we have the requirement, as usual, that we have regularity. That means here u has to be 0 in the center, and the Eulerian perturbation of the potential has to be 0 there. And at the boundary, we have, first of all, the condition that the boundary should be force-free. They are not unambiguous, of course, as discussed already before, but the correct version of the boundary condition is setting the Lagrangian pressure perturbation equal to 0. This does not mean that the Eulerian perturbation is 0, but we have to correct somewhat the Eulerian pressure perturbation to give an expression which is equivalent to the Lagrangian pressure perturbation to be 0. So Eulerian pressure perturbation plus displacement times the gradient of pressure has to be 0. This is the force-free condition, and the second condition is similar to that which we applied for the full system. Well, there should be a continuity of the potential to the vacuum solution of the potential, and this continuity, this continuous connection with a vacuum solution, this provides an additional boundary condition for the potential. So we have 4 boundary conditions again, 2 at the center, 2 at the surface, and we end up with a fourth order linear non-radial perturbation problem. Well, comparing these equations now with the radial adiabatic problem, of course, it's fourth order due to the gravitational potential. This is known. And as in the radial case, if we look for the coefficients which appear in our equation, there are the same, first of all, the same quantities. It's the pressure stratification, it's the density stratification, and it is the adiabatic exponent or coefficient gamma adiabatic. What we observe in addition to the radial case, of course, is the factor L times L plus 1. That's clear. That must appear because this is, we have non-spherical perturbations, but this is also the appearance of this quantity A and the gravity G. So if we look at the perturbation equation, we have the gravity here appearing and the expression or the definition of A. So G and A, this is new compared to the radial case, and we have also terms which go with L times L plus 1. This is the difference between the radial and the non-radial adiabatic perturbation equations. Okay. Now, I should perhaps mention here, the Ledoux-Wallraven formulation is one of the standard formulation of the adiabatic non-radial problem, There are also alternatives. There may be many alternatives, but one of the alternatives which is quoted very often is the Dzymbowski variables. It's just a different transformation of the system of equations. It does not change anything. It's just another representation of this equation in terms of different dependent variables, which might be more convenient in certain circumstances. So the Dzymbowski variables, well, Dzymbowski has introduced 4 variables, y1 to y4. The y1 is essentially the Lagrangian displacement. The y2 is something like the second variables of Ledoux and Wallraven. I remind you, P tilde over rho naught was essentially the Ledoux-Wallraven variable. He adds another term by using the potential, the Eulerian variation of the potential. Well, and y3 and y4 are essentially the potential, the Eulerian perturbation of the potential, and the gradient of the Eulerian perturbation of the potential. All these are normalized here by 1 over the gravity. Then he introduces some new combinations of the background coefficients. So the background model is described here in terms of a coefficient C1, which essentially describes the stratification of mass, and then U is also describing somewhat the distribution or the stratification of mass, whereas the coefficient V describes essentially the pressure gradient or the logarithmic derivative of the pressure gradient. And he uses another a slightly different variation or slightly different dimensionless frequency sigma. It's given by omega squared over the density. Well, it's essentially the normalization by the dynamical timescale, but it involves another numerical factor. So there's not much difference. And once we adopt this notation, then we end up with 4 equations, with a system of 4 first-order equations, which is given here. So on the left-hand side, we have r times dy1 to y4 by dr, and on the right-hand side, we have a linear combination of the dependent variables with the coefficients u, v, c1, a, and so on. So this is another representation which many people have used and many people are still using for the description of the non-radial adiabatic linear problem. Okay, we will keep to the Ledoux and Wallraven formulation in the following. Just for completeness, I wanted to show that this is an alternative representation of the Ledoux and Wallraven scheme. Now, first of all, let's consider Poisson's equation. This might be written in terms of second derivative of potential plus first derivative of the potential with respect to radius, plus a term that goes like L times L plus 1 over R squared of the Eulerian potential is of the order, or is given by 4 pi g times the Eulerian density perturbation. Now, if we estimate these terms to order of magnitude, then we will end up, if we express phi tilde, the Eulerian potential perturbation, then we will find that phi tilde should be of the order of 1 over L times L plus 1, or in the order of the density perturbation, the second derivative of the potential variation, and the first derivative of the potential. So the potential itself will be of the order of 1 over L times L plus 1. So this means if L goes to infinity, well, the potential will become small compared, for instance, with the density perturbation. And the Cowling's so-called Cowling approximation consists of neglecting the potential at all. So this estimate should give a reason or an argument when we can neglect the Eulerian potential perturbation as compared, for instance, with a density perturbation. This will be true for high values of L. An intuitive argument will be, well, if we have many nodes on our surface, then the potential, so to say, will average out the additional gravitational forces. Another situation where we can neglect the potential would be that the gravitational field is dominated by a core, and the pulsation will take place only in the envelope of the star. Then the small density variations we have in the envelope will produce only very small changes to the gravitational force, and therefore in that case we may also neglect the changes of force due to small density variations in the envelope. So, but one argument is if we go to large values of the harmonic degree, then we may neglect the gravitational potential. This is not true if we have low values of L, in particular for the spherical symmetric case, but we have no problem with the spherical symmetric case because in that case we have already integrated the potential and we have written it in an algebraic form, and so we don't need to consider the potential and the Poisson's equation separately as in the case of non-radial pulsations. So a quite common approximation in non-radial, considering non-radial perturbation, is so-called Cowling's approximation. We neglect the potential and its derivative completely. This has the advantage that the order of the system reduces from 4 to 2, and we end up with an equation which is at least mathematically comparable to the equation for radial adiabatic perturbations. Okay? So small-scale azimuthal perturbations will average out, and phi tilde may be neglected for large L, and this is the content of Cowling's approximation. Actually, there is not the Cowling approximation does not make a big physical difference because it's simply a quantitative change of frequency which might be seen, but not a qualitative change. It is physically, it does not introduce any severe approximation, and also it does not lead to substantial to very big changes in the spectrum of the star. Once you are interested, of course, in very precise measurements, then you should, at least for low harmonic degree pulsation, then you should, just for accuracy, you should not apply Cowling's approximation. Okay, the consequence is, the nice consequence, we will have less work because the order of the differential system is then reduced to second order. Okay, now coming back to the Ledoux and Wallraven formulation of our non-radial adiabatic system, we introduce, for simplicity or for convenience, we introduce from the variables u and v, u and y, we introduce new variables v and w by multiplying them by an exponential of the integral rho 0 g over gamma adiabatic p, and for the variable y and w, we introduce an exponential or multiply it with an exponential of the integral over our quantity a dr. Why do we do this? Let's go back to the equations. Well, of course, we now adopt also the Cowling's approximation, so we get rid of all these potentials, we get rid of the entire equation, and we get rid of the two terms here in the uppermost two equations. So what are we doing? Well, this reminds you of the integral over the integral which is appearing in the exponential in the transformation. So this is some kind of a diagonal term, and here is a diagonal term here which includes the coefficient a. To remind you, we had done a transformation exponential to integral over a integral over a dr. So these are the, so to say, the diagonal terms here. It looks as if they are anti-diagonal, but they are the diagonal terms. This is u, and this is u, and this is y. The aim of the transformation is to get rid of these diagonal terms, and this is actually explicitly done by the transformation, including the exponentials of the integral over the coefficients of the diagonal terms. You can convince yourself that if you do this, if you go to the new variables v and w, then these diagonal terms will disappear. Okay. Well, the transformation eliminates the diagonal terms on the right-hand side of the differential equation, and we are then finally left, together with Cowling's approximation, we are left with the two differential equations. dw by dr is sigma squared times the mean density plus the term, the expression GA divided by r squared times v times the exponential expression here, and the difference of these two integrals. And on the other side, we have dv by dr is the bracketed term involving L times L plus 1 over sigma squared. And here we have essentially the sound speed squared times w times this exponential. And observe the exponential here is just the inverse of the exponential in the second equation. They're just the inverse of each other. Omega squared is sigma squared times 4 pi g times the mean density. Okay, why did we do this? Well, we are now going to perform a so-called local analysis. What is a local analysis of a differential equation? Well, the local analysis consists of regarding the coefficients of the differential equation to be constant. What do we achieve by that? If we consider the coefficients of a differential equation, well, all the coefficients of our differential equation depend on the background model, or in other words, on the radial coordinate or on the mass coordinate. So they are not constant, and it's not easy to get a solution for that. But if you take or consider the coefficients to be constant, then linear differential equation with constant coefficients has exponentials as their solutions. In that case, we can adopt the solution of the form exponential of ikr, where k is some kind of wave number or 1 over the wavelength. So if we formally consider the coefficients of the differential equation to be constant, which is actually not true, then we can write the solution of the form exponential of ik times r. The question is, under which condition could we consider the coefficients to be constant? What might be a what might be a justification to keep the coefficients constant and look for solutions of the form of an exponential? What might be an argument? Consider this is the variation, for instance, of pressure P naught as a function of R, has some behavior like that, has a certain variation, scale of variation, certain pressure scale height. What might be a justification to consider this as a constant, or perhaps locally as a constant? Well, we take a small region here, and we compare it with the scale or the typical variation scale of our waves we are considering. Well, this describes a wave. If the wave number is very high, it means that the wavelength over which the typical quantities within the wave change rapidly. If this k is large compared to the variation of the background, then this might or could be a reasonable assumption. So what we are looking here essentially, or this approximation tends to consider small wavelengths or small wavelengths, short wavelengths, small high variations within the wave compared to the background, compared to, for instance, the variation of pressure compared with that of the wave. Okay, so this might be justified by the assumption or by considering the variations of the solutions, namely the wave, to be faster than that of the coefficient, that means of the background quantity. In these cases, if we do that, then we might have a reasonable solution. That means sufficiently short wavelengths are considered. Well, what we cannot do once we do this approximation, we cannot impose boundary conditions, because, well, we lose the boundary conditions by this exponential of IKR. We would have to impose a boundary condition at the very center, at the very surface. Of course, when it's going from the very center to the very surface, then the condition that the variation of the solution is much faster than that of the background is no longer valid. Expect to get a discrete spectrum for our modes. So this assumption also also tells us we cannot impose boundary conditions, and we do not consider a discrete spectrum as in the solution of the This is the characteristics of a local analysis, but rather we have we consider solutions of the form exponential of IKR, and let's see if we assume solutions of this type, what we'll get. Proportional to IKR, and with that and consider at least locally the background quantities to be constant, and let's see what we get for the wave number k. Well, doing that, we replace the derivative with respect to radius of w this exponential then can be cancelled from the equations, and we are left with an algebraic equation for W, V, W, and the rest of our coefficients. Now, I would like to remind you that these two exponential are for V in the upper equation, multiply the whole thing with ik, and then after some elementary algebra, these two exponentials cancel because they are the inverse of each other. On the left-hand side, we are left with minus k squared well, also, of course, the W itself cancels, and we end up with a relation between the wave number k and the other remaining coefficients. Well, it is a relation between k, and in particular on the right-hand side, we have the frequency formally kept or formally regarded as constant, and we will see in a moment how we can interpret this relation. So in the end, we get a relation between wave number and frequency. This is called, we have already seen such relations, this is usually called the dispersion relation. Depends on the other parameters of the system as well. This may be read in two ways. Either we consider this equation as an equation for the wave number k for given frequency, or we can also invert this and say, well, this is an equation for the frequency for given wave number k. We will consider this dispersion relation, this local dispersion relation, in both ways, considering it either as an equation for wave number for given frequency, or as an equation for the frequencies for given wave numbers. Can be read in both ways. Okay, of course we will hence in the following we will omit the subscript 0 to make the formula a little bit less crowded and less confusing. Okay, so we have dispersion relation, which may be read either as a function k of sigma or sigma of k. Of course, it also depends as a parameter the harmonic degree L, and because all these quantities depend on radius, also this dispersion relation depends also on the radial position we consider. P0 and ρ0 are functions of the hydrostatic model, and therefore the coefficients or this dispersion relation in general depends on radius, the parameter L, and on sigma, or vice versa. Sigma of k, L, R can read it also the opposite way. Now we have to distinguish according to whether the wave number is real or imaginary. We have a quadratic equation for k. If we prescribe the right hand side, then we can solve it for k. Well, the right hand side might be positive or negative, so we have as a root of the positive or negative value of the right hand side, k might be real or it might be imaginary, depending on whether the right hand side gives us a positive or a negative sign. When k is real, we have an exponential of ikr. If k is real, this describes oscillatory waves, and this is called an oscillatory solution. If k is imaginary, then we have exponential. We do not no longer have an oscillatory behavior, but we have an exponential behavior, so exponentially decreasing or increasing solution. In that case, we are talking about so-called evanescent solutions. This means distinguishes between real and imaginary values of the wave numbers. Keep in mind, K real means oscillatory solution, K imaginary is equivalent to an exponential, or in other words, evanescent solution. Okay, so this is the same dispersion relation, simply cutting out the W and somewhat rearranging this dispersion relation. In particularly, we have multiplied it with -1. We have taken out of the integral the factor minus GA, and we have taken out of the integral the value gamma adiabatic P over rho, taken out this out of the bracketed terms, and we end up with it's just a little bit of algebra which has to be which is applied with this dispersion relation, and we are left with this form for the local dispersion relation for radial adiabatic, for non-radial adiabatic perturbations. Well, there are two quantities appearing here which are new and which are given a new name, or which are defined in a new way. This is the factor minus gravity times the quantity A. I would remind you, the A was proportional to the entropy gradient within our hydrostatic background model. This has the dimensions of a frequency squared, and it's according to its discoverer, it's called the Brunt-Väisälä frequency. He was a Finnish guy, so it's pretty difficult to pronounce Väisälä. So it's I don't know whether I'm right. We call it Brunt-Väisälä frequency. Okay. So this is a new frequency appearing here, Brunt-Väisälä frequency, and the second frequency appearing here, or second quantity which appears here, which also has the dimension of a frequency, is the so-called length frequency. This is the frequency which appears here. It's gamma adiabatic times P over rho. We know this guy already. This is the sound speed squared. Sound speed squared divided by radius squared is a frequency squared times L plus 1. This is defined, or is called, the so-called lamp frequency. So we have in our dispersion relation, we have the lamp frequency here. So this is the ratio. What we have here is the ratio of lamp frequency over the frequency we consider, and this here is the ratio of frequency over the Brunt-Väisälä frequency, which appears in the first bracketed term. Okay, so that's for the definition we use. Well, I already said gamma adiabatic times P over rho is simply the sound speed squared. Okay, now, well, what is the physical interpretation? Okay, but once we can now perform two approximations to this dispersion relation. First of all, we put the terms GA equal to 0. What does it mean? We put either the gravity equal to 0 or the quantity A equal to 0. A was the entropy gradient. So what we are doing is we neglect the entropy gradient here. So if we put artificially GA equal to 0, what happens to our dispersion relation? Well, we have to multiply this in there, and then we are left with sigma squared times p over rho, and then we are essentially left with, so only one term is left here, and this frequency might be multiplied into this bracket. Then we have the Brand-Weiseli frequency minus the frequency. So we end up with another dispersion relation, which looks simpler, which is sigma squared minus Brand-Weiseli frequency squared 1 over sound speed squared is equal to k squared. Now solve that for the frequency. If we solve this for the frequency, then we see frequency is sound speed squared times k squared plus, well, the lamp frequency contains the factor L times L plus 1, L times L plus 1 over R squared. So the frequency is given by sound speed squared times wave number squared. This L times L plus 1 is some kind of azimuthal wave number, so this is proportional to L squared. This is the dispersion relation for sound waves. This is the local description, or is a local version of the description or the relation between wave number and frequency for a sound wave. Okay, this is so-called dispersion relation for sound waves. I have to finish here. I have to stop here. Perhaps I can just start a little bit. We can also do the opposite. We can, rather than asking for zero entropy gradient, we can exclude sound waves by putting sound speed to infinity. And if we do this, then if we put sound speed to infinity, then sound speed to infinity means we have to multiply this in here, and then this term 1 over sound speed squared will drop out, and we will be left with essentially the left bracket. And this bracket can then be written as k squared is Brand-Weiseli frequency minus sigma squared times L plus 1 over 1 over sigma squared. If we rewrite sigma squared in terms of omega squared, then we are left with omega squared. If we solve it now for sigma or omega squared, then we have this relation reduces to Brand-Weiseli frequency squared divided by 1 plus k squared over L times L plus 1 times R squared over R squared. This means this is the radial wave number over the tangential wave number squared. And the frequency by which we have the frequency wave number relation is a typical frequency wave number relation for the so-called gravity modes. The gravity modes live from Brand-Weiseli frequency, which is gravity and entropy gradient. Okay, so we end up in these two limiting cases. Once we exclude either the gravity waves or we exclude sound waves, then we end up either with a dispersion relation for sound waves or the dispersion relation for gravity waves. Okay, let's stop here, and we will continue on this subject then tomorrow.